angles, you could rewrite that as 2 sine x cosine x, and then make that cosine cubed x times sine of x. That would be cool to add in illustrating to the problem too, if you wanted to. I'm sensing no. So I'll just work it as is and say, okay, here's the first, here's the second. Product rule tells me y prime, or dy dx, is the derivative of the first. Derivative sign is cosine. Have to remember chain rule says to multiply by 2. That's the derivative of the first times the second plus the first. Now times the derivative of the second. And what most people forget whenever their cosine function is like this is that chain rule is what this is a group. Use a parentheses group. The group of cosine x to the second power. So you'd say, okay, power has to come down in front. It's going to be 2 times the cosine function to the first power times the derivative of what was inside of that group times the derivative of cosine, negative sign. Now, once again, we need to simplify. You cannot multiply terms of different angles, so can't do anything with that. So I'll just say y prime is 2 cosine squared x cosine 2x. And then this is going to make it minus. And I'll have 2 sine of x, sine of 2x. Put my double angles in parentheses. The only other thing you could do is factor out of 2, but that kind of be silly. What?
And you just lost 8 point, whatever point something.
0.3. Because, now
you get an extra credit.
Now I'm going to factor and say 2 cosine x times the group cosine x cosine 2x minus the sine of 2x sine of x. Ooh, I like that symmetry there. Gorgeous. Would you want to use a trigonometric identity on this?
No.
Do you remember what cosine, cosine, sine, sine is the formula for?
No.
Sure you do. Yes! Cosine of a plus b. This is nothing more than the cosine of x plus 2x. Cosine of x plus 2x is cosine x, cosine 2x, minus the sine of x, the sine of 2x. So you could simplify all this just to be the cosine of 3x. Oh, that would be gorgeous.
You get the formula, maybe you get there.
Nah, I wouldn't expect that. So we have y is equal to t over 1 plus the secant of t. Oh, by the way, guys, just so you don't feel like, oh gosh, although I don't think you'll be complaining about putting derivatives in the final because they're usually easier than intervals. But just to let you know that other classes have been doing this. I didn't think to do it all along. What Judy Fifi's class is doing, they must take what's called derivative review placement things throughout this. It doesn't impact their Calc 2 grade at all. It's just if they don't pass it, they can't get credit for Calc 2. So that she has like derivative criteria placement throughout this, and you get many, many chances to take it. So it's not like anybody who's passing Calc 2 is not going to pass those. But just to remind them, hey, you can't forget these derivatives. You can't forget these derivatives. She makes them take these placements throughout the semester, and If they don't pass them, then even if they're getting an A in calc, I can't imagine that scenario coming out. But if it did, they couldn't get credit for the class until they passed those Calc 1 derivative things. So I said, oh, okay. So it's not bad me putting it on the final go, John. And the reason I talked, she's our lead teacher for Calc 2. I want to be clear with her. Not that I need her mention. I thought I should. Okay, so looking at this, we have the derivative of this, and I'll say, well, what's the chain rule now? Chain rule, we know that we square the denominator, that's the low load. Yeah, did I not say quotient?
You said chain rule.
Oh, well, it is chain rule too, so I'm not wrong. I'm not wrong, I'm just not completely right. So thank you, it is quotient rule. So quotient rule, we square the denominator, then we say low d high. Low 1 plus secant x. D high. Well, assuming that, and I don't like that terrible notation, John. Terrible notation. I just did y and y. Boy, if you did that, I think I'd count the whole problem wrong. I'd just be like, I'm so insulted at your horrible notation. That's bad. I didn't even show that I'm taking the derivative. So I'm not even really happy with that. Because typically y prime is reserved just to represent dy dx. I should, if I'm trying to be neat, and I am trying to be, just not very successfully, say that this is dy dt. This is the derivative of y with respect to t. And so now, when I say, well, the derivative of the numerator, derivative of t with respect to t is 1. Low d high minus high t d low. Well, the derivative of the denominator. Derivative of the denominator, derivative of 1 is 0. Derivative of secant t is just going to be secant tangent. Secant t, tangent t. And the bad news is, I was thinking that this was chain rule too. There's no chain rule in this problem. Darn it. So now in simplifying, in my numerator I'll have 1 plus secant t minus t secant t tangent t. All of that divided by 1 plus secant t quantity squared. And I'm happy with that. Another quotient, or if you use the quotient rule, y is equal to x to the 4th plus the root of x. Over x squared. Oh, wow. I had intended this to be used the quotient rule. Do you see the more intelligent way to take the derivative here? Yeah. So the smarter thing to do here would be to say, oh, John, this is just x to the 2nd plus, this one would be x to the 1/2 divided by x squared. That'd be 1/2 minus 2, x to the negative 3 over 2 power. Oh. And then dy dx is equal to 2x, and then minus 3 over 2, x to the negative 5 over 2. Oh, I have an idea. Let's use the quotient rule and prove that we get to the same answer. Does that sound like a good idea? No.
Could you have just put y prime for that instead of dy dx?
Sure, since it's with respect to x. I think I want to do my idea.
Now, did you make us do that on the test, or?
Sure. We'll see how long it is. If it takes me more than 2 minutes, no.
But that would be done like 1 minute.
Yeah. So I like the comment, since the original was in radical, my final answer really should be in radicals. So this should be 2x minus 3 over 2 on the square root of x to the fifth, which then you could say is 2x minus 3 over 2. The square root of x to the fifth is 2 will go into 5 2 times. You can bring out an x squared, and you'd have the root of x left over. So that'd be a good final answer. Now, to verify that I get to that same answer using the quotient rule, I'd say, well, dy dx, quotient rule, I would square the denominator, x to the fourth, and then low d high. The low is my x squared times the derivative of the high function, 4x cubed, plus 1/2 x to the negative 1/2. That's low d high minus high x to the fourth plus x to the 1/2. D low, the derivative of the low function would be 2x. So as you can see here, a lot of terms will combine in that numerator. Well, first multiply, then combine, hopefully. I'll get my 4x to the fifth plus 1/2 x to the second times x to the negative 1/2. That's x to the 3 over 2. I think I'm almost to my 2 minus the group 2x distributed through this one. That'd be 2x to the fifth. And then x to the first times x to the 1/2 is x to the 3 over 2 power. All of this is divided by x to the fourth still. So now, please notice, in your numerator, 4x to the fifth minus 2x to the fifth, 2x to the fifth, 1/2 x to the 3 over 2 minus 2x to the 3 over 2. That's going to give me minus 1 over 2 minus 4 over 2. That's minus 3 over 2 x to the 3 over 2 divided by x to the fourth. Now if I distribute x to the fourth into both terms of the numerator, I would get my 2x minus 3 over 2. Whenever I divide, I subtract, so that's going to be 3 over 2 minus 4. That's like 3 over 2 minus 8 over 2. Negative 5 over 2. And we can see automatically this is what I had right there, which was so much easier the other way. But what I have here is what I have here, so I can get to that.
But that will be on the tax rate.
So, looking at number 5, if you want to use normal quotient rule number 5, I would welcome it, but you would have to reduce it down. You can't just do quotient rule and then not reduce your answer. And it would be pretty messy to reduce that answer because there's so many product rules going on within the quotient rule. So I would recommend in number 5, just go ahead, I'm going to rewrite it as e to the 3x and then x minus 2 squared over x plus 1 squared times x minus 8 cubed. And I don't know why that's a capital X. I made a mistake on my equation over. So now, before I try to take the derivative, I just say, I want to do this the smart way. The smart way is to take the natural log of both sides. And if this were a pre-cal class, I would show the steps in splitting this up, taking the natural log of both sides. By this time, we should be confident in saying, oh, there's going to be 4 logarithmic terms, any exponent is going to come down as a coefficient of each logarithmic term. So this first one is just going to be 3x times the natural log of e, and we know what's going to happen to that term, plus 2 natural log of x minus 2. What you should also remember is that any factors that are in the denominator, they're automatically always subtracted. So minus 2 natural log of x plus 1 minus 3 natural log of x minus 8. So now, this natural log of e, I remember natural log of e eliminate. So those are gone. And I have just the natural log of y is 3x plus 2 natural log of x plus or minus 2, all the way across. This is easy to solve now. So I'm going to go ahead and take the derivative. So I can say, okay, what's the derivative of the natural log of y? The derivative of any logarithmic function is 1 over what's inside the function times the derivative of what's inside the function. Now, here's where people would be thinking, but John, you should be taking the derivative with respect to x, because y is a function in terms of x. Yes, it is. Sometimes when we take the derivative of a variable and it's not the variable with respect to, you just say, oh, the derivative of that variable is 0. Clearly here, though, we can see that y is a function of x, so the derivative with respect to x is not simply 0. We don't know what it is, so we just say, oh, the derivative of y is dy dx. That's the implicit differentiation component. Now, over on the right, and keep in mind, you're always doing this. So we just don't think that we're doing it. Like when I say, guys, I need you to take the derivative of 3x to the first. You say, I'm going to be using the chain rule. 1 comes down in front, 3 times 1 is 3. X to the 0, so I don't put it, times the derivative of what's on the inside. So just please don't write this down because it's unnecessary, but you'd say 3x to the 0 times the derivative of what's inside. You'd say, well, the derivative of what's inside is the derivative of x with respect. That's why we don't put it, because the derivative of x with respect is just 1. But the derivative of y with respect is not just 1. We must put it. So here, this is the implicit differentiation idea. Anytime you take the derivative with respect to x, unnecessary, because there's just going to be a 1 from the chain rule component. If I keep on going, I'll say, so this whole first term is just 3. My next term's derivative of 2 natural log of x minus 2, 2 times the group, 1 over x minus 2, times the derivative of what was inside of that group, just derivative of x, which is 1. And then I'll say minus 2 times the natural log of x plus 1, 1 over x plus 1. Again, you could say times 1. Minus 3 times the derivative of the natural log of x minus 8, 1 over x minus 8. So now I can say, okay, dy dx is going to equal multiply by y on both sides. Y times what's on this right-hand side. You have 3 plus 2 over x minus 2 minus 2 over x plus 1 minus 3 over x minus 8. Would we want to stop there? Because we know what y is equal to, so you'd rather have your answer all in terms of x. So we'll say dy dx is equal to what we originally started with, e to the 3x, x minus 2 quantity squared, over x plus 1 squared times x minus 8 to the third. All of that times 3 plus 2 over x minus 2 minus 2 over x plus 1 minus 3 over x minus 8. Now, it is possible to distribute this fraction times every one of these terms over here and get even a better answer, I would advise against that. Though. It's just time consuming. So I'll just say, I'm happy with that answer. I've been writing everything down here, so we have a record.
Awesome.
Chris.
Awesome. Good job, man. Thanks.
Number 6. Right here, guys. The last of the derivative problems, sine x cosine y equals x squared minus y. Now, I truly think problem 6, we haven't used implicit differentiation hardly at all in Calc 2. You think, oh, it's been a while since we did that. I used a little bit in the last problem. And you might think, well, why is he doing this? It's going to show up tons of the times in future classes. Well, why? Because you're starting to deal with multiple variables, and also you're going to deal with things that are not functions. You're going to deal with things like x squared y cubed plus y to the 4th z to the 5th, to where you have to find other ways to take the derivative other than always explicitly having y equal to some function. It doesn't work that way most of the time. But it will work this way. So I can say, okay, how would I take the derivative of this function? Now, I need to be more specific, and on this I wasn't. I have to tell you, how about if I say I want the derivative of dx dy? I want to find the change of x with respect to y. Wouldn't that be awesome? Find, just to make it a little harder, not harder, just different. Find dx dy. Who says we always want to know the change of y with respect to x? You say that? No. I do.
But my question does relate to that. Couldn't you just flip all the variables and put it into something more?
What do you mean flip all the variables?
Like find dy dx of sine of y cosine x equals y squared minus x.
Well, remember, when you try to take the derivative of this side, you're going to have the product rule over here. It's not simply the derivative of the first and the derivative of the second. So I don't know if that exactly answers what... So what I'm saying is that you cannot solve for y other than some form of an equation having a y in there. So even if I changed my variables and just said, okay, what if I call the x, y, and the y x, I still couldn't solve for it because of the fact that it's out as a polynomial and in as an angle. Okay. Now, if you're saying I can find dy dx and then just switch my variables and I have dx dy, that's true. So, yeah. That'd be absolutely, you just switch them out. That'd be fine. But it still doesn't take away the fact we must use implicit differentiation. So on this one, I'm going to say, okay, if I want the derivative with respect to y, I say, well, clearly x and y are related. So I can't just simply say the derivative of x with respect to y is 0. I don't know that. I have to put dx dy in there in the equation for it. So I'll say the derivative of the first, derivative of the sine of x. Well, that's going to be the derivative of the sine function is the cosine function. Keep the angle times the derivative of the angle. You say, well, the derivative of the angle. I'm trying to find dx dy, so the derivative with respect to y, dx dy. So that's the derivative of the first times the second, cosine of y. Plus, product rule says plus, the first, the sine of x, now times the derivative of the second. Derivative of cosine is negative sine, keep the angle, so times the negative sine of y. And if I'm taking the derivative implicitly with respect to y, technically here I'd say times dy dy. But I don't want to do that because it's just a 1. You could. Is equal to the derivative of x squared. Again, I'll need to think of this as the chain rule. You'd say, well, the 2 comes down in front, times the group to the first, times the derivative of what's on the inside. Well, normally we just say the derivative of x is 1, so we don't do anything. Now, it's whatever dx dy is, times the derivative of x with respect to y. Minus the derivative of y, minus 1. So now, anytime you have an implicit differentiation problem, you want to get the terms that have the derivative remaining in there on the side by themselves. So I'm going to say, I'm going to pull every dx dy term to the left. When I pull them to the left-hand side, think about what would be remaining. This would have cosine x, cosine y. And I'm going ahead and factoring that because I can. Cosine, sorry. And then when I bring the 2x over, it's going to be a minus 2x. Now, set that equal to, what do you have on the other side? Well, this is going to become a plus when you move it to the right. So I'll have sine x sine y minus 1. So now what I am confident in saying is that the derivative of x with respect to y is equal to what we have on the right-hand side, sine x sine y. And we don't need the parentheses around that, though they're not bad. So I'll say sine x sine y minus 1 divided by cosine x cosine y minus 2x.
I'm not gonna try to solve for x and plug that in.
Yeah, I was gonna say, you're not gonna want us like solve for x or solve for y.
No. Remember, you couldn't solve for x or solve for y in the original problem. Now, what I think you may be remembering, and I remember putting a problem like this on the test, if I ever give you specifically an even function, and you take the derivative implicitly twice, you're guaranteed to have an expression that has the original equation within the answer that you can go back in and substitute for. Oh, it's gorgeous. I remember that. You can show that the second derivative of y with respect to x is equal to 15 over x. And you get this really long expression there. Like, how in the world does that equal 15 over x? And it's all because you just go back to the original. It's glorious. But now, so that was the derivative part. We want to look at the integration part. Now let me just ask you, does this seem okay? Pretty good? Alright. Now, probably I will not do dx dy. Probably I'll stick with dy dx. Same thing. We did that in this one. Or I like the point you made, Joshua. You could have just done it dy dx and just switched your variables at the end. That'd work. Number 7. So we have the integral of e to the negative 2x sine of e to the negative 2x dx. Now, this one actually, it could be a parts problem because Parts works nicely when you have an exponential and a trigonometric function in there together. But the problem with that is what they do is they cycle around. You'd have to take integration by parts twice to get that expression back in there, move it to the other side, and solve for it algebra. It'd be ugly. Not hard, just ugly. The way that you're supposed to look at this one and say, well, clearly, I'm going to let what's inside the trigonometric function be my u substitution. So if I let u equal e to the negative 2x, then I know that the derivative of u, the derivative of any exponential function, is that exponential function times the derivative of its exponent times the natural log of its base, but the natural log of e is just 1, so I won't put that. And that's with respect to x. So I don't see that negative 2 inside the integral. So I say, okay, then put it. I'll plug in a negative 2 inside the integral, and all of this is going to become du. Now, we know we can't just multiply by negative 2 on the inside without going to the outside, dividing by negative 2. So I'll say 1 over negative 2 on the outside. So now this becomes negative 1/2 on the integral. All of this part becomes du, and then this is just going to become the sine of u. We know that we can integrate the sine function and say, well, we know that the derivative of sine is cosine, but the integral of sine takes us back to a negative cosine. So this is going to be negative 1/2 times the negative cosine of u. And then I should go ahead and put my plus c, since this is an indefinite interval. And then, so this is going to give me positive 1/2 cosine u plus c. Substituting back in what u is, we can see that this is 1/2 the cosine of e to the negative 2x plus c. I think I know what you're thinking. You're thinking, wow, he's going to put this problem there, and then he's going to put ridiculously hard problems that do not solve by substitution on the final. I bet you're thinking that. I won't. No, I did. The last test was easier than your in-class. I swear by that. Especially the Taylor problems. You put those side by side with the in-class Taylor problems. Oh.
I will agree with you 100%.
Okay, guys. So, again, I'm kind of going in order. You think, oh, this is just an ordinary substitution problem. Yes. So you say, whatever is inside of a trig function was a u in the last one, or whatever's inside of a group is also an obvious choice for a u substitution. The horrible choice is if somebody said, how about I let u equal the entire group x plus 1 to the 1/4? It'd be nightmarish. But if you just say, let it be just what's on the inside, oh, it works nicely. We know that du is just dx, and at this point, some people think, oh, substitution doesn't work then. But we know it does, right? So, whenever you try to go back in and represent this, you'd be getting the integral of x times u to the 1/4 du. We know that that is not allowed. What do I need to do to get rid of this? Right here. So I can say, we know x is equal to u minus 1. So I can say this is nothing more than the integral u minus 1 u to the 1/4 du. So I'll get u to the 5/4 minus u to the 1/4 du. And whenever I integrate, I add 1 to the exponent, divide by the new term. So that becomes u to the 9/4 times 4/9. And then this one's going to become minus 4/5 u to the 5/4 plus c. And then putting in my final answer, and, I started to say putting it back in radical form, but the original form was fractional, so I'll keep it in fractional exponent form. But I'll say 4/9 times the group x plus 1 to the 9/4 minus 4/5 times the group x plus 1 to the 5/4 plus c. So a substitution problem in which you have to use algebraic substitution after the integral substitution.
Good question.
Yeah.
But that problem, I wanted to use integration chain rule, but it doesn't end up with the same answer.
Right. Yeah. Integration chain rule, remember for me, it would, if I just had this, it would work just fine. The problem is integration chain rule cannot handle that product in there. So if I would have something to address your question, Jordan, what if I would give you this? The integral of 5x plus 1 to the 1/4 power with respect to x. Integration chain rule works beautifully there. I'm sorry that's so ugly. But you'd say, well, it's just a group to a power, so the integration chain rule would tell me that this group is going to become 5x plus 1 to the 5/4 power times 4/5 down in front. And then you'd also divide by the derivative of what's inside. Divide by 5, make that 25. The difference there, Jordan, though, is that I didn't have that extra term out. Integration chain rule only works if that linear function is in isolation of the power. So anytime you have a linear function to a power, that integration chain rule does work. This one is more complex than that problem, though, because I don't just have a linear function to a power in isolation, I have that other function in with it. And I can't simply distribute through
What
either.
about in the previous number 7?
Well, no. Now, if I were to have had something like the integral of, let's say this, sine of negative 5x dx, that you could use the integration chain rule by just saying, well, okay, it's just a linear function inside of a trigonometric function. So you'd integrate the sine and get negative cosine, keep the angle, negative 5x, and then say divide by the derivative of the angle, like that. That'd be the integration chain rule. It's only for a linear term inside of a function. This one doesn't work. One, it doesn't work because even if that term's not there, you say, is what's inside a linear? No. Automatically doesn't work.
I just assumed that e to the negative 2x was the derivative of sine e to the negative 2x minus
Yeah.
the negative 2.
So what you're really doing, though, is you're doing substitution in your head whenever you're doing, which is fine. But that's not the integration chain rule. You're just doing substitution in your head, saying, well, that's just the derivative of that, so I know that that's going to get, yeah. Number 9. Whenever you see an algebraic function and a logarithmic function, what comes to mind?
Yeah.
Excellent. In fact, anytime you see a logarithmic function inside of an integral, hopefully you're thinking, Lyautey, this is going to be integration by parts. We know the very first thing we want u to be is a logarithmic function, so that's exactly what I'll do. I'll say, let u equal the natural log of x. Then I can say, well then I need to let everything else in there be dv. So dv is x squared dx. Now I need to differentiate u. The derivative of the natural log of x is 1 over x with respect to x. The integral of dv, integral of x squared, well, 1/3 x cubed. So now I can say, we know that the integral of x squared ln x dx is equal to u times v, 1/3 x cubed, natural log of x, that's u times v, minus the integral of v du. So that's just going to be minus, I'm going to put the 1/3 out in front, the integral of x cubed times 1 over x, x squared dx. This we can see simplifies really nicely. So it's going to be 1/3 x cubed, natural log of x. This again is going to be the integral of x squared, which is x cubed over 3 times 1/3. That'll be minus 1/9 x cubed plus the constant integration. Please don't forget that. These problems are not going to be too difficult. So, if you forget things like putting plus c, I'd probably count off 3/10, which I feel guilty doing that because it's pretty harsh. Number 10. So in 10 you have this is our second integration by parts problem. You have an algebraic function, sine of x, times an exponential function, 5 to the x dx. Any time you have a problem that looks like this, every single solitary time you have a trig times an exponential, you should be thinking this is integration by parts, but it's the cycle type. So I know exactly what's going to need to be done. I'm going to have to use integration by parts method twice, and in my answer, this is going to be a component of the answer that I can move over to the other side and then solve algebraically. Every single solitary time, that's the way these are worked. So I'll say, okay, the trigonometric function comes before the exponential, so I'll let u equal sine x. The dv is going to be the 5 to the x dx. We know that du, derivative of sine, is going to be cosine x, that's with respect to x. And that the integral of any exponential function, so now, if you were thinking, if I took the derivative of 5 to the x, you'd say it's 5 to the x times the derivative of its exponent, 1, times the natural log of its base, ln 5. We get so used to only working with e, we forget that part of our derivative formula. That only is unnecessary when it's an exponential base e. Any other base, we have to put it. That's the derivative, so the integral is the exact opposite. You divide by the derivative of that linear exponent, divide by that base, so this is 5 to the x over ln 5. Like that. Okay, so now I'll come down here and say, all right, so I know that this integral of sine of x, 5 to the x dx is equal to u times v. I'll go ahead and say that that's 1 over natural log of 5, because that's a constant coefficient, really, times 5 to the x times the sine of x. Order there doesn't matter. If you put in any order of those three terms, I'm fine with it. So that's u times v minus the integral of v du. I'm going to go ahead and say that that's minus 1 over ln 5. Go ahead and factor out the constant times the integral cosine x times 5 to the x. This is precisely what I wanted, because I know if I use integration by parts one more cycle, it's going to give me an expression with a sign back in there. So I'll do that. This time u is equal to cosine x. So du is going to be the negative of the sine of x with respect to x. And again, dv is the 5 to the x dx. And v is our 5 to the x over ln 5. Kind of gets repetitive. So now I'll say, okay, this integral sine x 5 to the x dx is equal to this. I'm going to write it as 5 to the x over ln 5 sine x. It doesn't matter. That's just condensed a little more. And then minus 1 over the natural log of 5 times the group. The group being everything that's in the integral of this, which is u times v. So I'll have, well, that's cosine times 5 to the x over ln 5. So I'll say 5 to the x over ln 5 cosine of x. That's my u times v minus the integral of v du. But I notice du is negative, so I'm going to go ahead and say it's plus the integral. And I'll factor out my 1 over ln 5 in front, and it becomes the integral of sine of x 5 to the x dx. At this point, I do see I'm pretty much done with the problem. It's just algebra. The calc part, done. It's just algebra from here on. I'll get the integral of sine x 5 to the x dx is equal to 5 to the x ln 5 sine x. I'm going to distribute this 1 over natural log of 5 through, and I'll get minus 5 to the x over the natural log of 5 quantity squared. Please don't get that confused. A common mistake students would make is they'd say, oh, that's the natural log of 25, 5 squared. That is not 2 natural log of 5. It's the group natural log of 5 quantity squared. Can't do anything to that. Times the cosine of x. And then I would have minus, again, 1 over the group natural log of 5 quantity squared on the integral of the sine of x 5 to the x dx. Okay, so on the other side, I know I'm going to need to move this term over, and it's going to become plus 1 over the natural log of 5 quantity squared. Technically, I could call the coefficient of this one the natural log of 5 squared over the natural log of 5 squared. That's just an understood 1. So when I move this term over, my numerator is going to become the natural log of 5 quantity squared plus 1 over the natural log of 5 quantity squared. All of that times the integral sine of x 5 to the x dx. I'm liking this problem. That's equal to, I only have these two terms on the right-hand side now. And I'm going to go ahead and factor the 5 to the x natural log of 5 squared out. When I do that, my first term, I factored out a natural log of 5 squared in the denominator out, which means this term has a natural log of 5 left in it as not in the denominator. You would have had to multiply your numerator by natural log of 5 in order to ensure that your denominator is natural log of 5 squared. So I have natural log of 5 times the sine of x. Now on this side, the entire thing canceled, and I just have minus cosine x. So the goal to the end of the problem, solve for your integral of sine of x 5 to the x dx. So we can say, we know the integral of the sine of x 5 to the x dx is equal to 5 over the natural log, oh that's 5 to the x, I apologize. 5 to the x over the natural log of 5 quantity squared. I'll go ahead and say times the reciprocal of this side. Oh, this is gorgeous. The natural log of 5 quantity squared over the natural log of 5 quantity squared plus 1. Times this group, natural log of 5 times the sine of x minus cosine x. So now you see algebraically the natural log of 5 quantity squareds cancel, and your fully factored final form of the fantastic answer is 5 to the x over natural log of 5 quantity squared plus 1 times the group. Oh, and I think I'm just going to put that group in the numerator. Yeah. Natural log of 5 sine x minus cosine x. And I'm going to go ahead and put that natural log of 5 in a parenthesis. Otherwise, it looks like the natural log of 5 sine x. Wouldn't that be? Oh. Yes, yes. Thank you. Indefinite integral, put your plus c. Now, it's not needed until that step. All the way up here, I still have my integrals in there, so it wasn't needed until that step into this step. That's my new absolute favorite problem that we have on the final so far. That's the first, what I would say, arguably hard one. 11. So you have the integral. Again, now if this looks a little odd, what happened is I was making out your final exam review as I was giving a test yesterday, and the room I was in that I was giving the test, it didn't have math type on it. So I had to use Microsoft Word Equation Editor, which is why it looks a little different than it normally looks. And I'm not very good at using Equation Editor. I like math type. Bad there. That should be x squared on the square root of x squared minus 9, all under the square root. Say that again. Oh, yes. Yeah. Oh, yeah. We don't want to do that. So I'll say this is dx. Yeah, I bet you're thinking, wow, he just wants us to simplify a little bit there. X squared on the square root of x squared minus 9. It will be typed out better.
You sure?
Now, what do you do on this one? Anytime you have a variable squared minus a constant squared, secant. So this is x squared minus 3 squared, so automatically you say that's in the format where you let x equal 3 secant theta. If it were 9 minus x squared, 3 sine theta. If it were x squared plus 9, 3 tangent theta. Okay, that's your 3 trig substitutions. Could be any one of them. But now, if we know that x is that, then dx, the derivative of secant is again secant tangent. So this will be 3 secant theta tangent theta with respect to theta. Now, before I go back into the problem, I would recommend going ahead and thinking about what all these terms are. When we know x squared is simply going to be 9 secant squared theta, x squared minus 9 is going to be 9 secant squared theta minus 9, which then you could factor the 9 out and call that 9 times secant squared theta minus 1, which that's one of our Pythagorean identities. Secant squared minus 1 is tangent squared. So this is 9 tangent squared theta. So I have my problem set up. I'll say this is simply, so I'll say the integral dx over x squared on the square root of x squared minus 9 becomes the integral. My numerator dx, 3 secant theta tangent theta d theta, my denominator x squared, 9 secant squared, on the square root of x squared minus 9, which would be 9 tangent squared theta. The square root of that, 3 tangent theta. So now, I know that the tangent of theta will cancel in the numerator and denominator. One of the secants cancel, so I know that this is going to be left with, and this 3 can cancel with this 3. I'm going to factor the 1 over 9 out. So the 1 over 9 factors out, and I'll be left with 1 over secant to the first inside there. And then we say, but secant is nothing more than the reciprocal of the cosine, and I will promise. And if I'm not good on this promise, it means you can skip the problem and it won't count against you. But the promise I make is that you won't have to know any of those power reduction, double angle formulas, anything like that. The only formulas I will hold you to are the Pythagorean identities, which those are very easy. Just if you ever forget it, put down sine squared plus cosine squared is equal to 1 and algebraically reduce it to whatever you need, if you happen to forget. But the only trig identities you'll need is the Pythagorean identities. And, of course, knowing the reciprocal identities, 1 over secant is cosine. So you're not going to end up with cosine squared, which you have to rewrite as 1 plus cosine 2 theta. If you know that, fantastic, and that's wonderful, and it will help you. But I'm not going to do that on the final, because I'm feeling a little too nice. Cosine theta, d theta. So this is the integral of cosine is just sine. Wow. This simplifies a little too nicely, doesn't it? 1 over 9 sine of theta plus c. Do we want to stop there? Of course not. That'd be terrible. Because the problem was in terms of x. Your solution needs to be in terms of x. So here's where we say, okay, use the fact that we know, we use the substitution, x is equal to 3 secant theta. 3CO. 3CO. There you go. So I know that that means x is equal to 3 times 1 over cosine 3 over the cosine of theta. Okay. I would have preferred just to say x over 3 is equal to the secant of theta. That would have been better done. And then say, so the cosine of theta is equal to 3 over x. I like that better. I could have got to that by what I had right here, but this is cleaner. So I'll say, okay, my right triangle, here's my theta. The cosine of theta is adjacent over hypotenuse, 3 over x. So please remember, your other leg is always the square root of the hypotenuse squared minus the other leg squared. So x squared minus 9. And if you're double checking, the side you're finding always has to be a part of the original problem. So if you messed up and said something like x squared plus 9, and you look to the original and said, oh, I know that's not right. It can't be. It has to be that x squared minus 9. So now, I go back in and I try to represent my answer. My answer is supposed to be 1/9 the sine of theta, opposite over hypotenuse. So 1/9 the square root of x squared minus 9 over x plus c. And I'll just go ahead and say this. X squared minus 9 divided by 9x plus c. Are we okay with that one? So last one. This one should be extremely familiar because it's our integration by parts. And you'll see that that was intended to just be x minus 3 squared and x plus 3. Oh, actually, I'm going to leave it as it is. Let's work with it like that. I like it. We haven't done one like that. You're like, oh, is that, wow, is that, actually, it did. Let's see if you think it is. So all of ours had constants in front of the x's, and you think, is that, or sorry, had a 1 in front of the x. Is that going to make any difference? Not really. I'm going to treat it as it is, but what I was saying, that I guarantee you it will be a type of a problem where we have a repeated linear factor. I will not do quadratic factors. They will be linear factors. But when I say repeated, you could have a third power in there. We have to say a over the group to the first plus b over the group to the second plus c over the group to the third. Could happen. But it will be linear repeated factors. Those cases occur with much more frequency than the others. I don't put it on there because it's easier. It is easier, but I put it on there because that case occurs more frequently. So I'll say over x minus 3 squared. And I'm going to leave, that was an unintentional 2x plus 3, but I'm going to leave it. Okay, so first thing I would do is I'd say, well, we're going to let 4x squared minus 21x over this x minus 3 squared times 2x plus 3. That has to equal a over x minus 3 plus b over x minus 3 squared plus c over 2x plus 3. So, yeah, go ahead, John.
Quick question. Does it matter what order you put them in?
Absolutely not. Now, your answers for A, B, and C, like if you put C as over x minus 3, then my answer for A will equal your answer. But it doesn't matter whenever you start plugging it back into the problem.
Okay.
It'll be the same. So now I'll say, okay, if I multiply by the least common denominator on each side, I'll get 4x squared minus 21x is equal to, so I'll have a, and a is going to be multiplied by x minus 3 to the first and by a 2x plus 3. B is going to be multiplied by only the 2x plus 3. And C is going to be multiplied by x minus 3 quantity squared. So, guys, if I wanted to solve for B, what would you let x equal? 3. So, if I let x equal 3, on the left-hand side, I can say, well, it's going to be 4 times 3 squared minus 21 times 3. That's going to, the A would be times 0, the C would be multiplied by 0, and the B is going to be multiplied by 2 times 3 plus 3. So on the left-hand side, I have 4 times 9 is 36 minus 63 is equal to 6 plus 3 is 9b. I'm getting 9b is equal to 36 minus 63, that's negative 27. So 9b is negative 27, thus I can say b is negative 3. Now I need to try to solve for A and C. And I can say, okay, it's fairly easy to solve for C. You'd say, what value would I let x equal if I want to get rid of terms A and B? Excellent. You just say, hey, if x is negative 1.5, then 2 times negative 1.5 is negative 3. Negative 3 plus 3 is 0. Cancels out both A and B. So I'll let x equal, negative 1.5 is fine. I'm going to call it negative 3 over 2. And I'll say, okay, on the left-hand side, I'm going to have 4 times negative 3 over 2 squared minus 21 times negative 3 over 2. That should equal, over here, I'll have C times negative 3 over 2 minus 3 quantity squared. So on the left-hand side, I know that this is going to be times 4 divided by 4, so that's just going to, these two are just going to cancel. And I'll have negative 3 squared is 9. And then minus 21 times a negative 3 over 2, so that's going to be 21 times 3 is 63, 63 over 2, so plus 63 over 2. That's going to equal C. Now, 3 is the same thing as 6 over 2, so I'd have negative 3 over 2 minus 6 over 2. That'd be C times negative 9 over 2 squared. So on the left-hand side, 9 is the same thing as 18 over 2. So I get 18 plus 63 is 81 over 2. And nice! The right-hand side, I'll get 81 over 4C. Thus, C is equal to 81 over 2 times 4 over 81. C is equal to 2. Now, of course, if you did that on your calculator, you take those many, many steps I did and make it done in about 5 to 10 seconds. But I think it's kind of fun to get to it.
Or instead of making this.
Oh, yeah. You could do that. And I'm certainly not one to frown on matrices. I like matrices. I think this is fun too. So I have A, I have B. Sorry, no, I don't have A, darn it. So I have B, I have C. Now I need to find A, and all I would need to say is that I know that A and C, they're the only coefficients of an x squared term I would have. B cannot equal a coefficient of x squared. over here, if I multiplied my x terms, I would get 2x squared times a. So I can say 2a is a coefficient of x squared. I know 1c is a coefficient of x squared. So 2a plus c must equal the coefficient of x squared, 4. But we already know c is 2, so I get 2a plus 2 is 4. Thus, 2a is 2 and a is 1. Now, all I need to do is say, so the original problem is equal to a over x minus 3. So this original problem is 1 over x minus 3 with respect to x, plus b, which is a minus, so I'll say minus, I'm going to go ahead and pull that 3 out in front, times 1 over x minus 3 quantity squared dx. And then the c was a 2. I want to leave that 2 inside there. So I'll say plus 2 over 2x plus 3. Guys, does it make sense why I pulled the 3 out in the second one and chose to leave the 2 into the third one?
Yes.
Yeah. You always want to see the derivative of the denominator in the numerator. So this last one is just going to be the natural log of 2x plus 3. This first one is just going to be the natural log of x minus 3. My second one is not a natural log because the degree difference in the numerator and denominator is 2. What I can do on that is like what Jordan was talking about earlier in class. That's just the integration chain rule. I have a linear function to a power. That understood power is the negative 2 power. So this second one I'm going to think of as x minus 3 to the negative 2. That's going to integrate to, I know when I integrate, I add 1 to the exponent, x minus 3 to the negative 1, divide by that new exponent, and divide by the derivative of the inside, which is just 1. So now I should be able to simplify this first term. Anytime the derivative of the denominator is in the numerator, natural log of the denominator. This second one, it's going to become negative 3 divided by negative 1, so plus 3. And this x minus 3 to the negative 1 becomes x minus 3 in the denominator. Plus, that 2 is eliminated, so please don't put 2 natural log. The derivative of the denominator had to be in the numerator in order for it to be a natural log. So I'll say it's the natural log of 2x plus 3 plus c. Didn't forget it that time.
John, a question about the middle part, or when you're getting your A's, B's, and C's.
Yeah.
If you've got like a particularly ugly one and you're down to your last variable, can you just pick a value for x and then plug in your A's and C, all your other terms and solve?
Because if you already have the other one solved for,
Yeah, like it's the last ugly one with sure.
Yeah, you could do that. But now it's always easier to pick a variable that will cancel those other terms out. But if you can't do that, then yeah, you can plug anything in. Yeah. So that was our final exam review done in, what, an hour and a half?